So the requirement for computer networking, we can look at, if we look at the definition of, of computer network, we can describe it as follow. A computer network is basically a shared platform through which a large number of users and applications communicate with each other. So there are some key words, which the first one is shared, and then large. So you want to share. You don't want to dedicate. You don't want a dedicated platform, and the number should be large. And then you want to communicate. So then you talk about three issues from this definition. You talk about the connectivity, because you want to communicate, so you need connectivity. And then you talk about who and how to connect. And you talk about, because you talk about a large number, so you talk about the scalability, how many to connect. And because you're talking about a shared platform instead of dedicated platform, so you'll talk about the way to do resource sharing. That is how to utilize the connectivity. So we'll center around the requirement on these three requirements: connectivity, scalability, and resource sharing. And especially on resource sharing, there are two ways to do resource sharing. And you will see that traditionally in the data communication society, we use packet switching. But in the telecommunication society, in the traditional telecommunication society, they use circuit switching. So I call, why do I say we and for datacom and they for telecom? Because datacom is winning, so I want to stand on the winning side. So I'm saying datacom for we and telecom for them. And so compared to circuit switching in the telecom, consider a telephone call, a traditional telephone call from traversing the traditional plain old telephone system. That if you have a phone call from A to B and passing through 10 telephone switches, what happens is that within each switch, within each link and each switch, you would need to reserve the bandwidth. The bandwidth on the link and also the bandwidth on the switch. The bandwidth on the switch means that you need to occupy a table entry, to memorize who is from which input you switch to which output. So you need to occupy the bandwidth on the link and also the node, okay, throughout the phone call. So if the phone call lasts for 10 minutes, then the bandwidth occupied will be reserved there for the entire 10 minutes. But throughout the 10 minutes phone call, A only speaks a half of the time, because the other half, A will be listening from B. And B the same. B will be talking a half of the time, but a half of the time it will be listening. So at least the reserved circuit bandwidth is only 50% utilized, because half of the time I'm listening, I'm not speaking. But when I'm not speaking, my bandwidth in this direction is still reserved for me, and nobody else can use it. Okay. So I occupy the bandwidth within the circuit throughout the phone call, even though I'm not using it. So compare, circuit switching, then you immediately see the circuit switching is not a very efficient way to share the bandwidth or to share the resource. Okay, but at least it's about 50% utilized, right? But things could be worse. If we are talking about data communication instead of voice call, if this is a file transfer, an email transfer, or a web access, then the traffic will be bursty, By bursty, we mean when you need it now. But most of the time, you don't need it. Okay. So then if I use circuit switching and do the data communication, then most of the time the bandwidth will be reserved but not used. But only a part of the time I would have data to send. But whether I'm sending or not, the circuit is reserved for me and nobody else can use it. So you see the circuit switching will be only 50% utilized when used for phone calls, because half of the time you are speaking and half of the time you are listening. So your transmission bandwidth will be 50% used. But for data transfer, instead of voice transfer, the utilization will be even lower, because most of the time I'm not using the link, the bandwidth. Okay, so probably the utilization will drop to like 10%, even though the bandwidth is reserved for me for the entire duration. So circuit switching is not an efficient way to share bandwidth, especially for data. It's probably okay for voice, but definitely not okay for data. So you definitely need to use packet switching that you don't occupy the bandwidth, you don't reserve the bandwidth. You just send a packet and compete for the bandwidth. Okay, so that's the idea of packet switching and circuit switching. And there are some more elaborated discussion on this in the text. Okay, and so we talk about three issues: connectivity, scalability, and resource sharing. And the connectivity, so another version of connectivity definition is a connected platform constructed from a set of nodes and links where any two nodes can reach each other through a path consisting of a sequence of nodes and links. So here we talk about link, node, and path. So these three. So we'll talk about node, link, and path. So a node can be a host, the end host, the very end of the internet, or the gateway, in the middle. So a node can be a client or a server or a peer, or the node could be something in the middle, which is networking node, which is the router, switch, gateway. These are the interconnection devices. These are the node. And the link could be classified into two categories. One is a point-to-point link, and one is a broadcast link. By point-to-point, we mean only 2 endpoints. Only two nodes can use this link. That's point-to-point. And for broadcast link, there'll be many attached points. So there'll be many nodes that can use this link. And what is a path? A path is a concatenation of node and link. So if a path is 10 hops, there'll be between A and B, there'll be 10 link and also 10 node in between. Okay, that's a concatenation of links and node. However, a path can be classified into two kinds of paths. One is the routed path, and one is the switch path. And what is a routed path? What is a switch path? That in the text we have a elaborated description. Let me give you an example why we call a routed path is a stateless concatenation, while the switched path is a stateful concatenation. Here the term stateless and stateful is important. Stateless meaning that you don't memorize something, but stateful means that you memorize something. Consider traditional telephone network from A and B, user A and B, and they they have a phone call passing through 10 telephone switches. And consider another scenario, which is also user A and B, but now in between there are 10 IP routers in between, 10 IP routers. So 10, a pair with 10 telephone switch, traditional switches, and a pair with 10 IP routers. What are the differences? Okay, on the telephone switch, remember that we say you reserve the bandwidth for the phone call. And the path is switched, not routed, meaning for each telephone call from an incoming input port, I need to memorize, I have an entry, table entry, which is sometimes called virtual circuit table or circuit table or some other names, So I have a table memorized, for each call incoming from which input port. I should switch to certain output port. And the circuit number, incoming circuit number should be changed from a certain number to another number. And that kind of mapping from input port to output port, that kind of mapping is memorized, it's kept in the table entry. So there's an entry to memorize that. So throughout the phone call, if it lasts for 10 minutes, I have a table entry in each of the 10 switches to keep track of this phone call. So I'll memorize, from input port number 3, and if the virtual circuit number from that input port, I look up the table, I found out that, it should be switched to output port number 7, and with the circuit number changed from 10 to 12, for example. So I will have a table entry to keep track of that. And within this 10 telephone switch, I have a table entry for this call. So if a telephone switch has, say, 10,000 phone call passing through, it would have a table of with 10,000 entries. And each entry will memorize the mapping to keep track of this. And why do we need to keep track of this in the telephone switch? Because we want to do what? With just one index. From input port number 3 with the virtual circuit number 10, I would index into, say, table entry with index into table entry number 3, and then entry column number 10. So I will see what the entry tell me. The entry tell me that I should switch to output port number 7 and change to the virtual circuit number 12. So I could just index by just one index to know how to switch the voice to another output port. And indexing is just one memory access. Indexing is just one memory access. It's a table with 10,000 entries, and I have a number 3, or say 3,000. I would just look up that address, and with just one memory access, I can grab the information I need to do the mapping. So it's just one memory access. So with this kind of switching, that'll be very fast. The switch between input and output port will be very, very fast. However, the disadvantage is that I need to keep track of these table entry. And these table entry are called the state, the so-called state. And another scenario in the IP router, I don't keep the state. I don't do the switch, I do routing. And what would I do? I would take the packet coming in, and there's a header. In the header, instead of a virtual circuit number, I see the address. And the address is, say, IP address in the header. destination IP address. I'll take that address and look up a table, and this table will tell me it's so-called routing table, as we will see later in the later chapter. That you take the destination IP address and look up the table and do the matching, and then eventually you find out, okay, the next hop. Okay, then you know, okay, which output port I should route the packet to. However, that table, that so-called routing table, the size of that table is independent from the number of calls or the number of connections passing through this router. The table could be large or small, but it's independent of how many flow or how many connections passing through. So you cannot consider that routing table as a state. And actually, I don't keep the state of the connections. Okay, so I would just look up the table and then find out the output port, and then I put it into the output port. And that process is called routing or forwarding. Okay, and I don't memorize the state for, say, these 10,000 connections passing through. If I'm a router and there are 10,000 flows passing through, and I don't keep the table entry for each of them. I don't. Actually, I don't keep the table entry for them. I don't keep the state for them. So it's called stateless. And I do have a routing table so that I can tell, okay, where the destination could be. So I need to do the table lookup. And within the table lookup, it takes a longer time. Instead of just one memory asset, I would need to do the matching. As we will see in chapter 4, you will see that the table lookup, routing table lookup, is implemented as an array of hash tables. So you will look up a hash table or array of hash tables. And when you look up the hash table, you need to do what? You need to do computation. You put the destination IP address into the hash function, do the computation, and then the hash function will give you a value, say 12. And then you index into the entry number 12, and then you start to do the matching with the IP address. You do the matching with the IP address there, and you match. So there'll be, when you do match, you do what? Comparison. You compare two words in the CPU. You do the matching. You do the comparison. So you would involve with computation, involved with memory access, because when you look up the table, you need to do memory access. And then you need to do comparison instructions. And there are studies showing on the average, to look up a routing table, it would take 7 memory access and 7 comparison instructions on the average. So 7 memory access and 7 comparison instruction. So that would apparently longer than switching. In switching, it's just 1 memory access. Okay, so in the routing, does a router know? Okay, does router memorize? Say I have 10,000 connections passing through. Does a router memorize or keep the state of these 10,000 connections? No. The answer is no. It does not keep the state. I don't have a table entry for each of these connections. So we call the routing. The routed is a stateless concatenation, and we don't maintain the state information for each particular connection. But in the switching, in the other scenario, we have an entry for each of them. So that's why. So in comparison, switching is fast, but has overhead, especially the memory overhead, that you need to keep track of the state, the mapping state from input to output. However, routing is slower because you need to have multiple memory access, multiple comparison, but no overhead to keep the state. Okay. And both kind of scheme has a routing table so that they know where the destination is. So both have the routing table, but switch need to have another circuit table, mapping table, which does not exist in the router. Actually, the term switch has been used, sometimes misused. Say, you will see layer 2 switch, layer 3 switch, layer 7 switch. There's a common P4 at the end of the chapter 1 about that switch, layer 2, layer 3, and layer 7 switch. And I would say that in the telecom world, when people talk about switch, it might mean the telephone switch traditionally. But in the datacom society, when you talk about the switch, you would talk about the devices that would keep state. Say in the layer 2 switch, they also keep state for a particular flow or connections. Layer 3, okay. But sometimes they misuse, say I have a layer 3 switch and a layer 3 router. What's the difference? Sometimes they misuse to mean that a layer 3 switch, it means a hardware-based solution, but they do routing in hardware. But layer 3 router means they do routing in software. Sometimes they misuse that. And so commonly you will hear a term like layer 3 switch or layer 3 router, but probably they mean the same thing. And probably they differentiate them into layer 3 switch for hardware solution and layer 3 router for software solution. But they probably don't differentiate that much. But I would say that the better way to differentiate is that a switch is an interconnection device that keep state about the flows passing through, the connection passing through. However, a router is a stateless device that does not keep track of the connection passing through. The terminologies are not that well standardized. So in the datacom, if you see people from the telecom society, or you see people from a datacom society, they probably talk about the same thing in different terminologies. And I would say that so in the common P4, we have discussion on that. Yeah, please look at that. If it depends on whether the state is hard state or soft state. As we will see that in this chapter later, quickly, that you will see ATM is hard state and MPLS is soft state. By hard state, it means that the state will be kept there unless you disconnect, unless you clear up to disconnect the connection. Otherwise, the state is there. Okay. But by soft state, which is MPLS, the state will time out. Meaning, if the state is now refreshed within the period of time, it will time out. So what happened is that in the situation you mentioned that if there's a link failure, if it's hard state, then it would not do it would need a mechanism to reroute the connections. It would not do it automatically. Okay, but in MPLS, if there's a disconnect, it's possible that you have no packet going through, so the state will expire by itself, and then you establish a new a new route. Okay. For IP router, the same, because there's no state. So you would do the rerouting automatically. So you don't need to clear up the state. No state to clear in routing, in IP routing. But in MPLS, you don't need to clear the state either, because it would time out later on. Okay. But we will talk about that concept very soon. Any other question? Okay. So we talk about the node link and path, and we spend some time on a lot of time on path and the routed path and switch path. And I hope you would catch the idea of the stateless and stateful. If this is quite new to you, please look up the book section describing that. And for host, you can have small computer or large computer, from mainframe to handheld to set-top box, to your cellular phones. These are the clients. Or there could be some large machines, which are the servers. And there could be intermediary devices from hub, switch, router, gateway. And they need to process packets. And usually they need to process at wire speed, or they are expected to process at wire speed. And so they are usually embedded systems. So router, switch are embedded systems, usually with special IC, integrated circuit for speed up or cost reduction. So they are usually not general purpose computer for those switch and router, and they are mostly depends on how big they are. They could be, the price could be less than $100 to several tens of thousands of US dollars. So depending on how small or large they are. But they are all embedded systems. And the main goal is to process packet fast and probably at wire speed. Okay, for the link, the point-to-point link or the broadcast link. We mentioned that a point-to-point link has only two endpoints. And then you have the issue of whether they can, which side can use the link, send the data. It could be simplex, meaning that link is only used for one direction. Or half duplex, meaning it could be used in both directions, but one at a time. Or full duplex means in both directions at the same time. Okay. And point-to-point link are usually used for wide area network. Okay. That's point-to-point. And for broadcast link, it's usually for LAN, local area network. But there are, of course, some exceptions. For example, the satellite-based Aloha, it's a broadcast link, but it's definitely not local area network, because the satellite is far away. And there are also exceptions for WAN, point-to-point link. Some of the point-to-point link are not used for wide area network, but used for local area network. For example, the Ethernet switch. Well, Ethernet was used to be broadcast link, but later on it turned to a point-to-point link. And we will talk about that evolution to point-to-point link in chapter 3. Yeah, in chapter 3. But wireless LAN remain as a broadcast link, and it's for local area network. And usually the broadcast link has the issue of multiple accesses, meaning they need to compete, they need to contend to access this broadcast link. Okay, and for a link, we can divide it classified into wired or wireless links. Okay, for wired link, you basically have three kinds of media: twisted pair, coaxial cable, and fiber optics. For wireless, you could have radio, microwave, or infrared, depending on how high or how low the frequency is, or the spectrum is. And we will talk about this wired and wireless link, the media, in chapter 2, in the physical layer. And in chapter 2, we also cover the coding and modulation scheme for wired and wireless link. And we will talk about the point-to-point broadcast link in chapter 3, in the link layer. So PPP is a protocol for point-to-point link. We'll talk about that in chapter 3, and also we'll talk about the Ethernet here for broadcast link, and Ethernet evolved into point-to-point link later on. And we'll talk about wireless LAN, and Bluetooth, and WiMAX. These are broadcast link. And WiMAX, you would say WiMAX is a broadcast link, but it's not LAN. It's for first mile. It's not within hundreds of meters, but it's within several kilometers or tens of kilometers, the last mile. So these are covered in chapter 3, and these are covered in chapter 2 with more details. And there are some popular wired and wireless link technologies that I just mentioned. That for the local area, you have wired and wireless, and for the last mile, again wired and wireless. For the lease line, they are all wired because they are usually used in the backbone of the network. So they are wired, but if the backbone could use some wireless link, but compared to the wired backbone link, the bandwidth is too small. So most of the internet backbone now are wired link with high bandwidth. And say 10 years ago, before 2000, these are the mainstream. Before 2000, these are the mainstream for the backbone. But now the backbone, the mainstream is this: gigabit, 10 gigabit. Gigabit and 10 gigabit are the mainstream for the internet backbone. Okay, here is another page describing give you more detail about routed and switched. And I just explained, but this page gives you, I think, a better summary on that. So a routed pair is stateless, and it's a connectionless concatenation, and each message is routed independently. And because it involves matching the destination address against the routing table, and that requires multiple memory access and address comparisons, so it's slower. In comparison, a switch pair is stateful and is a connection-oriented concatenation. And at an intermediate node, they need to memorize something, keep the state in the table entries. And the plain old telephone systems have all the telephone calls switched. And switching is faster because it's an easy index into the switching table in just one memory access. Okay. However, the overhead is that you need to keep track the table entry, and you need to do connection setup first. On the internet, you don't do connection setup. You can send just one packet on the internet, and the router will forward for you. You don't need to set up a connection on these routers, because these routers look at your IP address and check the routing table with multiple memory access and comparison, and then find out which will be the output port to forward. So this router will do this the forwarding for you without connection set up. However, in a telephone switch, you need to set up a connection first before you can send the first packet or the first data. And the connection setup is actually establishing the table entries. So I'm establishing the table entry. The table entry means the mapping between input port and output port. I need to set up this table entry when I do the connection setup. So I need to establish the state if it's a switched code. Okay. Okay, here there's an example. Two examples here. And I have just, I should explain it here on this page, but I just explained it on the previous page. So I don't want to explain again. So two examples, a flow passing through 10 routers versus a call, a phone call passing through 10 switches. And another example will be a router with 10,000 flow passing by, and compared to a switch with 10,000 phone call passing by. So think over these two and compare them. You will see the difference. Okay, so now let's take a break. To see why ATM faded. One is historical evolution. There are three kinds of sidebars in this book. One is the historical evolution. One is principle in action, and the third type is called performance matters. So I remember that, where's the book? There are 33 historical evolution sidebars, and 26 principle in action sidebars, and 10 performance matters sidebars. And most historical evolution sidebar are about the history. Okay, all the evolution ongoing evolution. But this is history. The ATM, which was dead in around the year 1998, 97, 98. It was designed as a technology, a synchronous transfer mode. ATM could stand for automatic telling machine, but here it's not. A synchronous transfer mode, which is a core technology that was designed for so-called broadband ISDN. And it's the technology developed by the Telecom Society, by them, okay, not us, okay. They developed the ATM for broadband ISDN, broadband integrated service digital network. Integrated ISDN was the solution developed by Telecom Society in the year of 80s, and in 90s they developed broadband ISDN. And the idea is ISDN or broadband ISDN, they try to merge the phone call with the data application. So on the same network, I try to carry phone call and also the data. And in ISDN, they try to carry the phone call, the voice call on circuit switch network, and carry data network, packet switching network for data. So they have a unified interface but separate network internally, one circuit switching and one packet switching. But in broadband ISDN, they try to have again unified interface, a flexible interface, but internally one network. So only packet switching network, no more circuit switching. So in the 90s, when they developed ATM, they know the telecom camp, they know that they need to take the packet switching technology. They need to forget about circuit switching technology. So they develop packet switching technology, which is called ATM, asynchronous transfer mode. And it's packet switching. However, it's a stateful switching. It's not routing, meaning that you need to set up a connection first. And especially that connection need to reserve bandwidth. That connection comes with bandwidth and is stateful. So you need to memorize so that you establish the connection, you set up the state, and then once you start to pump the packet, they will do the switching fast. And that's called ATM. And that's good. It's packet switching, which is good in terms of resource utilization. And it's switching. So in addition, except the overhead to do the connection setup and maintain the state, you can switch the packet fast, which is a good thing. So we can do that to carry for both voice and data. Okay, so it should survive, but it didn't survive. Why? Because in 90s, the TCP/IP is already there, developed by the Datacom Society, by the Datacom camp. So the internet is already there. Remember that in the year 1993, that was the year WWW was developed and then started to get popular. That was 1993. The reason I remember this is because that was the year I graduated, got my PhD from UCLA. So that was 1993. And so before that, the internet has been around for a while, since 1969. That was the first node of the internet. So it's based on TCP/IP, and it's what? Stateless routing. So it has been stateless routing. And ATM solution came up by the telecom camp, but they came up late. They came up to find, okay, the IP is already there everywhere, though not as everywhere as today now, but in the early 90s, it already prevailed across the globe. Not that commercial, but more academia at that time. Okay, so the ATM technology is stateful switching, but the IP camp, the Datacom camp, is IP routing, stateless. So this came up late, so they need to coexist with the internet. At the beginning, they want to build their own broadband ISDN network by those telecom operators. But they realize, okay, it might be too late to do that. So instead, they probably need to coexist with the internet first. But to coexist, it's a problem. It's a huge problem. Consider this here in the Datacom, in the IP world, in the IP network. If you want to send packet, do you need to set up connection first? No, you just send a packet. No connection set up. No stateful. No state kept in the router. Okay, but you take a longer time to do the routing, right? To look up the routing table. But here in ATM network, you need to set up, you want to send data, you need to do what? Set up a connection first. And the connection needs to be switched, which means that the state for each connection. So what if ATM is the core, however IP is the edge? What will happen? You want to send a packet from A to B across the ATM network, then you need to just to send one packet. You need to set up a TCP ATM connection first. and then send the IP packet across, and then tear down the ATM connection. Okay, and that's a big overhead because you just want to send one IP packet, but you need to set up the ATM connection, which is a big overhead. Or the other way, that instead of ATM as the core, but you embed the ATM into every IP node, for example. So that would be the solution I just mentioned is called internetworking. That is a problem, right? And the other solution will be layered hybrid, meaning that every node will support both IP and ATM, with ATM at the lower layer, but IP at the upper layer. So that'll be, in the protocol stack, that'll be IP over ATM. Then what happened is the same. If you want to set up IP packet, then you still need to set up ATM connection first, and then send the IP packet. And once you finish, you tear down the ATM connection. Okay, so you still have that kind of overhead of establishing, send the data, and then later tear down. And if you do that, that would, and you try to replace IP router by this kind of IP over ATM devices, then you destroy the nature of connectionless or stateless nature of the IP routers. Within the internet, with IP router, they are stateless, connectionless. But now, if you have that kind of IP over ATM inside the internet, the core of internet, then this core of internet will become what? Connection oriented and stable. And that changed the nature. So the to coexist IP with ATM is painful with a lot of overhead. So in the year of 97, the telecom camp, especially the service provider, well, the equipment provider is still struggling to push this kind of solution. But the service provider, because they have played around this kind of device products for quite a while, and they know the overhead is too high, simply too high, another problem. So they declare that they give up. Okay, that they gave up this kind of solution. Okay, so then all the equipment provider providing ATM switch, they just went bankrupt. They just went broken. Okay, because that wouldn't work. And that's the time that Cisco continued to enjoy the happiness in business. So the internet continued to grow. So you know why Lucent was acquired by Alcatel? This is one of the big mistakes they made, because Lucent invests a lot on this kind of broadband ISDN ATM solutions. And if this really take off, then Lucent will be the king. However, this solution failed, and so it collapsed. So Lucent lost a lot of investment, and eventually they couldn't afford to go on, and then got acquired by Alcatel. And Cisco continued to grow for say 10 consecutive years, but in recent years they slowed down. Okay. So that's the reason why they wouldn't coexist well. So it's like a couple, a male, a female couple. If one is very outgoing and one is very not outgoing, then they wouldn't coexist well, and the marriage will eventually break up. So similar thing. They wouldn't. I don't know. At that time, the research community before the year 97, 98, the research community was crazy. with generating tons of papers on ATM, and later on they start to realize the overhead for this kind of coexistence is simply too high, and then given up. But at that time, they are not, the investment is not just on the industry sector, but also on the academia sector. Okay, so we talk about the connectivity, the routed connectivity or switch connectivity, and I urge you to think over the routed connectivity and switch connectivity. And I'm going to stop here.